That's number 3 of the Shock Show. And I want to invite everyone to share this content. This is information on and examples and demonstrations on basic understanding of ultrasonics and piezoelectricity. Talking through a mirror here, we're going to be sharing the screen. This is YouTube Live, so this is getting a little bit interesting. So I wanted to go in this third episode and continue the theme, which is understanding why we have non-symmetric resonance responses. And the second reason, the first one was that the coupling factor and the quality factor were low. But the second reason, and this is still going with linear theory, is that there are multiple modes which exist in your device, and these multiple modes sometimes coincide with each other. And I'm going to demonstrate here a live example on my laptop, which is why I'm using a mirror to kind of show myself here. I'm going to demonstrate an example from a buzzer. It won't be perfect, but it'll demonstrate the point. So two resonant modes can coincide. And especially if this piezo material has low Q, then the resonant oscillation will be of multiple types, despite locking on to a single mode. So there are a few ways that this is caused in practice. One of them is that, for example, if you're designing a longitudinal transducer, that you have other modalities existing. So you have bending modes, you have other. Let's say you're designing a longitudinal transducer, you have a screw mode. In the Langevin type transducer. So you have other types of resonances and ways that sound can bounce back and forth in your system in order for that to be two resonant modes on top of each other. The other ways that this behavior can occur is through defects. So the defects can occur either through non-symmetry. So if you have two discs, let's say you're bonding your piezo disc to a metal shim, that the anti-symmetry, the non-symmetry between those two components can cause additional modes. Due to slight differences in symmetry that are very similar to the operating mode, but then take away from the amount of excitation you can achieve in any one of them. The other issue can be assembly defects. So one example is epoxy. So many devices are epoxy together, but the bond strength across the entire material may differ. So other aspects of assembly may also come into play, which causes imperfections in your actual device. The next is surface defects. So surface roughness, that also includes flatness. These may also cause these additional resonant modes to come into play. And bending modes especially are susceptible to these spurious modes, to these non-desirable resonance characteristics. So you have a resonance response, but you actually aren't able to achieve the desired state or as much energy into the desired mode and as you would like. So let's take an example here. Let's take the mirror away, and ta-da! So we have here a piezo buzzer, and I'm going to generate and run its frequency response from 3 kilohertz to 5 kilohertz, and the blue response is the impedance. So you can actually hear it because it's in the resonance frequency range. Now, this wasn't a perfect transducer for what I was looking for. I was actually looking for the resonant frequency to get right on top of the operating one. If we assume this is the operating mode, like we designed our buzzer such that it would be the loudest with the same voltage at about 3.8 kilohertz right here. But there are additional modes, and at times these modes add to the variability of the transducer because they can move around based on, again, defects in assembly tolerances, concentricity, and surface conditions during that assembly and bond condition. So this is an example from a piezo buzzer. It's not exactly on top, but this behavior can vary. And when it does vary, and when it does land very close to the resonant frequency, it can cause a distortion in that behavior. So you won't be able to use, again, your quality factor calculations from 3dB to able to analyze it. The equivalent circuit will start to get sketchy at that point. So how can you continue to analyze this transducer despite its weaknesses in obeying single mode behavior? So now we're not only talking about linear behavior, we're talking about single mode behavior, which allows us to use some of the equations that we're familiar with. So in order to analyze this, let's say if you had a spurious mode at resonance, there's spurious mode like a sharp, another peak or another value right here, then you can also opt in to use the anti-resonance for analysis. So you can get a better linear response or single mode activity analysis. Just like you can analyze the equivalent circuit at resonance, you can also do that at anti-resonance, and also would describe the transducer in general at that point. And this may also be important because oftentimes the anti-resonance is plagued with, in this case, it might also be plagued with another closed resonant mode. In that case, you can use the resonance frequency itself and only parameters from the resonant frequency to determine an equivalent circuit and to determine a theoretical anti-resonance from which you can calculate a coupling factor. And the other thing to do here is, if you are evaluating prototypes, look for prototypes that don't have multiple spurious modes around your resonant frequency. Now you can design some of this into your FEA analysis using modal analysis to investigate what modes might exist, because experimentally they do exist. Even if in FEA it's usually you have really perfect symmetry, perfect bonding, but in practice, because you have variability in bonds and intolerances, you may get additional modes you may not have thought to predict in harmonic analysis. The other thing to do when you have this behavior, and especially for bending mode resonators, it's really hard to get away from this type of behavior. Then if you are stuck with it, then what you can do to analyze this is rely less on impedance and more on system level tests. So for a buzzer, you may detect the frequency of maximum mechanical oscillation. So you could either do that through sound measurement, you could do vibrometer measurement, because vibrometer is a single point measurement. It is more sensitive to isolating single modes of analysis. So you can produce because there may be for example, for this buzzer, there may be an additional mode here that doesn't really move a lot of air, but still it detracts from the major resonance. So because it doesn't move a lot of air, let's say it doesn't produce a lot of sound. Therefore, you can use instead of doing impedance, which impedance is, given a voltage, how much current is going to flow. The lower the impedance, the more current. And that transfer function you can also do as an output, like sound level over input voltage. This is obviously current, voltage over current, but you can provide this frequency analysis in whatever way it allows you to continue to evaluate their transducers. So looking and emphasizing system level tests more may be important in sort of getting that to a more ideal state. So thank you for watching number 3 of this series of the Shock Show. Please look in the comments for additional links to my consulting offerings, as well as a course in impedance analysis that I offer. It's an online video course, and I look forward to seeing you in the next video. Thanks for joining.